Uniform convergence is actually quite handy when it comes to talk about interchanging limits. We've seen an example of a sequence of functions, xn, 1 minus 1, 1. We had a limit, pointwise limit, given by this function f. And one of the things we noticed is that fn converges to f on the interval minus 1, 1. Fn is continuous, f is not continuous. Fn is differentiable for all n, f is not differentiable on account that it's not even continuous, so it can't be differentiable. If you look at this example here as well, so each member of the sequence is given by n squared x. X is between 0 and 1 over n. It is minus n squared x minus 2 over n. X is between 1 over n and 2 over n, and is 0 otherwise. While these functions converge to function f on the interval 0, 1. Which function could it pointwise converge to? You don't really have a choice. It has to be function 0. You're not sure, convince yourself that this is indeed the case, but it's basically the same argument as what we saw here. If you look at the integral of the fn's between 0 and 1, you will be able to show it's 1. The integral of f over the same interval as 0. When n goes to infinity, the integrals of the fn's do not converge to the integral of f, the limit. When I talk about interchange theorems for the limits, what I'm talking about is the fact that the limit of the integral should be the same as the integral of the limit. At least this is something we would like to see. None of the convergences here are uniform. They're all pointwise convergence, and that's the real problem. When you have uniform convergence on some set f, then if the fn's are continuous, so is f. If the fn are differentiable, so is f, and on top of that, the derivative of the fn's go to the derivative of f. If the fn are Riemann integrable over the interval a, and so is f, and the integral of the fn's go to all of f. So these will be the three theorems that we will prove. Let the fn's be functions from a to r that are continuous for every n. If fn converges uniformly to f in a, then f is continuous. Alright, so we prove continuity. Let epsilon be some arbitrary positive value. We know that there's some integer which here depends on epsilon over 3, such that the difference between fn at x and f at x is less than epsilon over 3 for every x in a, whenever n is greater than x. How do we know that? Make sure you understand which assumption is at play. Then we pick some value c in a. By the triangle inequality, the distance between f at x and f at c is going to be smaller than or equal to the distance between f at x and f h epsilon 3 over x, is this index here, plus f h epsilon 3 at x minus f h epsilon 3 at c, plus the distance between f h epsilon over 3 at c minus f at c. We know that the first one of those is smaller than epsilon over 3. I wrote n epsilon here, but obviously I meant this index right here. So this is smaller than epsilon over 3. That's what we have above. It's pointwise convergence. This bit also smaller than epsilon over 3 for the same reason, right? C is one of the points in A. And then we're left with this quantity right here. But this function, f h epsilon over 3, it's one of the fn's. So it is continuous. In particular, it's continuous at C. So this here would be smaller than epsilon over 3 whenever x is in A, and x minus c is smaller than the corresponding delta epsilon over 3 for that specific function. This is by continuity, f h epsilon over 3. What this is telling us is that the specific delta epsilon over 3 that works here, the specific delta epsilon over 3 that satisfies the continuity of f at h epsilon over 3, whenever x minus c is smaller than that distance in absolute value, and whenever x is in A, then we have f x minus f at c is smaller than epsilon. In other words, f is continuous at c. Did you figure out why this was true? In particular, why this h epsilon over 3 did not depend on the value of x? It is because we have uniform convergence of the fn's over f, right? This is absolutely necessary. If we did not have this uniform convergence, this value here would depend on x. You'd have a different threshold for every value of x, potentially. And here, this would screw this up completely, because the h epsilon over 3 that you would have, when you try to simplify or find a bound for this distance, would depend on the value of x. You wouldn't be able to use the same argument. That being said, it's important to remember that you can have Fn converging pointwise on A, Fn continuous, and F continuous as well. It's just that if you want to guarantee that this is going to happen, you require, according to Theorem 67, that the convergence actually be uniform rather than just point.